So like I said before, kinematics is the mathematical study, right? Or the mathematical study of motion. And you're going to see that there's really two parts here. And the way it's going to be broken here is that now, one of the things that we're going to do here is that we're going to focus much more on graphing motion. And then the other thing that we want to do here is that we need to master the kinematic equations. And you're going to see that there's really only 4 equations. Okay? There's really only 4 equations that we want to focus on. And these are them right here. So our goal here is to master these equations. And because there's only 4, it turns out that we can develop techniques that you will always pick the right equation, assuming that you get the physics right. If you don't have the physics right, you don't have any chance of getting to the right equation. Okay, so that's really the important piece here. We want to get into this here. And before we get started here, what we want to do here is that I want to remind you, even though I've said this before, we will only consider constant acceleration situations up to the first exam. And the reason why is that if you don't have constant acceleration, it's mandatory differential equations that you have to solve. But that's beyond the scope of this course here. So in other words, this is possible this will not happen. Okay? That will not happen here. So what we're going to do here is that you're going to see here is that the first thing that I want to do here is that I need to interpret drawing motion diagrams to represent the motion, because it's a powerful technique as well as plotting. Okay, so the first thing that I want to do then is that I want to interpret graphical plots here. So let's go do that. So now our first thing that we want to do here is that we now want to interpret graphical plots of motion. And when I say that, what I'm really talking about is I'm talking about plotting position, velocity, and acceleration versus time, all simultaneously. It is so important. This semester, I am teaching Engineering 15, and Engineering 15, you're going to find here is that there's a lot of plotting that students are actually doing right now. So there's a lot of plotting that's going on, and it's something that comes up in Physics 4B, 4C, 4D, and everything else. So you want to really pay attention that this is super important. So let's go look at this. What we want to do here is that we want to do the following thing. So when you look at the kinematic equations, what you're seeing here is that if you look at these guys, look what happens. Note that the highest power of time is t squared. So if it's t squared, that means that there's only, so if I want to represent any of the kinematic equations, we only look at power functions. So if we only look at power functions, that means that all of these functions are going to be some constant times some power to n. So when you're looking at this, we're going to say that this guy is typically a constant, and n could be 0, 1, or 2, nothing more than that. So the position has that. So if you look at this in terms of trying to understand what these look like, check it out. I know that velocity, as far as a derivative is concerned, is the rate of change of distance. And if you go and you look at one of these equations right here, and if I bring these kinematic equations over here, what you're seeing here is that if I look at the position, here's the position equation right here. So that position equation essentially says this here, that if I take the derivative of the position, it's going to be x naught v naught t plus 1/2 at squared. And the initial values and a are always constants. So I'm going to get 0 plus v naught plus at. So in other words, I re-get that graphical question that we just answered in the previous chapter here. And if I go in and I look at the acceleration and I take the derivative of the velocity, the same equation here, you could see that this will be v naught plus at. And if I take the derivative of this, again, v initial and a being constants, you're finding that I get back the original acceleration equation. So it's not like we're doing, great algebra. All I'm showing you here is that these equations are consistent with our definitions. With our definitions that acceleration is velocity divided by time, and velocity is the displacement as a function of time. So all of these equations can be derived from these things here. So what I want to now focus on is that I want to look at the plots for each situation here. Okay? So let's go look at this thing. And so what we find here is that I want to then go look at plotting these motions here. So I'm going to break these up into cases, but I want to show you where all of this is located at. So what I did here is I wrote, if you go to the website, let me share my screen. You see that in green, I have this thing called Plotting Motion Review Handout. So if you open that link, here's what you're going to see. Okay, you can download it or you can preview it. And if you do that, here's what you're going to find. So what I did here is that I went in and I started saying, let's look at these curves. What does it mean if I plot position, velocity, and acceleration? What is the slope of the position? What is the slope of the velocity? And how are all of these points connected, which we'll go over. And then I broke it up into constant velocity with its motion diagram, and then cases of acceleration with their motion diagrams. So you really got to master these things here. These will pay huge dividends throughout the semester. Okay, so I want to go through these and try to help you understand what this is. But note, you have access to this, okay? You have access to this because you can download it from the website. So let's go look at this thing now. So the first case that I want to look at these things here, I want to look at case 1. In case 1, I want to talk about V equal to a constant, velocity equal to a constant. So we've done this somewhat already, so let's focus on this thing and try to move through it somewhat quickly here so that it's real, so we could really spend most of our time on acceleration. Well, according to our definition, if V is equal to a constant, that immediately implies that the velocity does not change. So the acceleration is a constant. And what we've said before here is that if the acceleration is a constant, then that means that we use this relationship to plot position. And what we found here is that we can plot position where we have plus or minus an equation like this. So if I look at this equation here, I could then go in and plot this thing. So what does this look like? Well, what we said before here is that if I have a plot, I don't think I want to make it that large. How about if I make it a little bit smaller? So I'm going to try to plot these right on top of each other. So I'm plotting position, velocity, acceleration. So here we go. So if I look at, here's my plot. So now I'm going to look at the motion diagram. And what we said here, if we have an object that's moving with some velocity like this, and its acceleration is equal to 0, then we have equally spaced dots and the velocity does not change. So what that means curve-wise, that I have a positive slope. Why? Because it's moving in the positive direction here. Now, on the other hand, if I have a velocity that's moving in the opposite direction, I can draw this with vectors that look like this, and I'm trying to draw them all the same size, then that means I'm headed in the negative direction, so it has to have a negative slope here. So that's what we mean by those curves. So what do I know? Well, I know that the velocity in red is then going to be positive, right? This will be my constant velocity here. And my green velocity is going to be negative, but that's still constant. It's a negative value. And the accelerations in this case, they're both going to be what? 0. So this acceleration is 0, as well as this acceleration is 0. So that's exactly what we expected this thing to be. So now let's go look at our next case. We want to look at constant acceleration here. So if we do that, I'm now in case 2. Okay. And here we now have acceleration equal to a constant. Okay, so when we look at this thing here, note that there are really 4 different situations. So there are 4 possible situations. Now, one of these is going to be like this here. You can have a velocity to the right and also have acceleration to the right. In other words, you're speeding up. But note, you can also have a very similar situation where I'm doing what? My velocity is to the left, but my acceleration is also to the left. So that looks different graphically than the other one, but it should still mean the exact same thing. And the other situation where now we're slowing down. So I could be going to the right with an acceleration to the left, or I could have a velocity going to the right with an acceleration, velocity to the left, but an acceleration to the right. So these are the four possible situations that we want to think about. So let's go graph these four situations. Okay, so I'm going to try to draw my graphs here. Let's see, something like this. So I got position, velocity, acceleration. So let's look at this thing here. So let's talk about the cases of speeding up. Speeding up to the right. Well, if I'm speeding up to the right, what do I know? Well, for starters here, we know that our arrows must be getting longer, right? And the only way this could be possible here is that if I have an acceleration in this direction. So what we said before, if I'm speeding up to the right, which I'm going to call my positive and my negative direction then clearly what I'm seeing here is that speeding up to the right implies that you're having an increasing slope. So if I'm increasing slope, I'm looking at my velocity and it should be constantly curving up like this here, right? So the slope constantly increases here. So I should say that the slope constantly increases. Positively. Now, if I increasing in speed in the negative direction, then that means just the opposite. I'm seeing my velocity vectors getting larger in the opposite direction. So when I look at this velocity, what you're seeing here is that in this case, you know what, I'm going to bring this down just a little bit. I want to put some words in here. So now I'm speeding up to the left. So, but I got to be careful here. So this is increasing slope in negative direction. So when I'm looking at this guy here, then my slope should be going in the opposite direction, right? So in this case, I have a slope constantly increasing in the negative direction or negatively. So what does that mean? Well, according to our equation, if velocity is changing, then velocity must be, according to what we said, plus or minus AT. So that means if I have a positive increase in velocity, then that means I have to have what? My slope of this guy is positive. So in other words, when I look at my slope of this guy, A is positive. And that means here in this situation that I have what? Velocity and acceleration in the same direction. But if I look at increasing in speed in the opposite direction, it's going to look something like this here. So in this case, we say that the slope of A is negative. And in this situation, we're seeing that the velocity and the acceleration are pointed in the same direction this time. So when I look at the acceleration values, since I have a constant slope, right? This is what this guy is telling me here. This guy's telling me right here that this is the slope value. Then my positive acceleration has a constant that's positive. My negative acceleration has a constant value that's negative. So whenever you see situations that you're accelerating in the negative or positive directions, pay attention to what those slopes must be looking like. Okay, so we've talked about speeding up. Let's talk about slowing down now. So here we go. So in this case here, I need to draw 3 more curves. So let me draw them. So I have position, velocity, and acceleration. So if I just scroll up here very briefly, we just talked about speeding up. Now I want to talk about slowing down in different directions. So here we go. So now what we're doing here is that we're going to be slowing down, going to the right. So if I'm slowing down, going to the right, then our picture then says this here. Well, my velocities are getting smaller because my acceleration is in the opposite direction. And remember, for simplicity, we can draw this like this just as easily here. So if I'm looking at this thing, that means here that the slope of this guy, this implies here that the slopes must decrease. So let's look at this thing. So if I look at my curve has to have a slope that's decreasing. And when I look at my slopes of my velocity, what should I do here? Well, if I look at my slopes of the velocity, what you're seeing here is that you're seeing the slope here, and then you're seeing the slope there. You're seeing that the slopes of this guy is getting lower here. So if you do that, then you could imagine that if my slope is decreasing, my velocities must be decreasing. So according to our definition here, our velocities must be going from a higher value to a lower value, right? So I have to have a decrease. So I'm seeing that my velocity and my acceleration are in opposite directions. I'm going towards a lower. And when I look at my acceleration clearly then states that it must be what? A constant negative acceleration. So I'm going to do the same thing for the other one now. So now I'm slowing down going to the left, which then tells me here is that the slopes, here, let's draw this first before I get there. So when I look at this guy here, I now have what? Higher to lower to lower. And this is because now my acceleration is in the opposite directions. So the slopes must be getting what? They must be getting less negative. So the slopes must be getting less negative. In other words, they must be getting more positive, if I could say this. So when I look at my curve here, my curve then says, wrong color, it's got to be doing something like this. And so when I'm looking at my slopes, you could see that this slope is steeper than, let's say, that slope right there. So there's a decrease in slope, but a decrease in slope says that my velocity must be doing this here. In other words, if my velocity is in the negative direction and I have a positive acceleration, it must look like this. So therefore, I have a positive acceleration here. So what we want to do is that we want to go in and we want to practice this with on some examples here, but there's a couple of things that we really want to talk about here. Okay, so there are problems that are in between. What about problems where you have motion that changes direction? Okay, so there's a couple of things that I want to do before we move on here. So we've talked about the two main cases. So now I want to look graphically at situations that change direction. So what's a good example of changing direction here? So let's say that you have a situation where you're moving to the right, but the acceleration is to the left, and then you stop and turn around and then continue to move in the direction of the acceleration. So let me go plot these things. I'm hoping I'm giving myself enough space. I may not, actually, I think I'm not. I think I need more space. Let me do this. I think this one's going to be, so this is A, V, and X. So let's look at this thing here. So now what we're going to do here is that if I look at this situation, let's imagine I'm going to the right and I'm slowing down. So that means I'm going like this, like this, like this, and then here I stop. So at this point right here, you stop. So if I'm looking at my velocities, I'm looking like this. Clearly, my acceleration in this case here is then going to be to the right. But now what happens at this one point right here is that there's a change in direction. But if I keep a constant acceleration, what you're going to see here is that then I'm going to start to speed up again. Because I'm still moving under this constant acceleration. So what you're seeing here is that this is a turning point where an object changes direction. how does that look graphically here? So if I stop, clearly the speed at that point must be 0. But remember, anytime I have a speed of 0, the slope has to be 0. So here we go. So let's pick this point right here along this line. And I'm going to put this line all the way through here. Okay, so this is the point where I'm going to say that the slope is 0. So what I'm seeing here is that if I'm slowing down, I'm seeing that my slope is changing, it's changing, it's changing. And then right here, what does it do? It's flat. So that means when I look at my slope here must be 0. But what does slope mean of 0? It means that it what? The slope means here that you have 0 speed. So that means here at this point that the speed v must be 0. So then the car is now speeding up. So you can see here is that my curve is getting steeper and steeper, steeper velocity as we set up here. If you're speeding up in the negative direction, you got to be doing this. You could see that I sort of like piecewise there. So what does this mean here? Well, if I look at the velocity is decreasing. Okay, so here I go. My velocity is decreasing all the way down to here. Okay, as it decreases, it's going to go from here. And then what happens? It stops, right? The speed goes to 0, but then it continues to speed up. And you could see that the speed is getting faster and faster. So picture-wise, what you're seeing here is that my velocity up here is in the positive direction, but down here is in the negative direction. But in each of these situations, what you're seeing here is that the acceleration down here must be opposite, whereas the acceleration here is positive. So look at the acceleration. It's pointing the same direction. It's always negative. So you could see that the acceleration is a constant, but it's negative. So there's a couple of important points here. Okay. If velocity is positive, then the object is moving to the right. So look at this thing. How do I know that this thing is moving to the right? Because look, it has a positive value right here. How do I know that the object is moving to the left? Right? So if v is less than that, then the object must be moving left. So look at this. If you're in this region over here, this region here tells you you're moving to the right. This region is telling you you're moving to the left. So any negative velocity on a curve means you're moving left. Any positive value for the velocity, you're moving to the right. But note, the slope is 0, meaning the velocity is 0 right there. So now I can do the exact same thing if I'm going in the opposite direction. So here we go. So now if I look at this situation, and then what do? I stop right here. In other words, my speed is 0. And then what am I going to do? I'm going to turn around. So when I'm looking at my velocities, you could see that they're decreasing. Why? Because the acceleration is in the opposite direction. And then I start my speeding up process. And you could see that I'm getting faster and faster and faster because of the acceleration. So what does this mean picture-wise? Well, picture-wise, that means I know that I have to stop. So at some point, I have to have a slope of 0. So my speed is decreasing. So therefore, so what's happening to my slope? It's getting less negative. And then right here, what do I get? I need a slope of 0. Now that I have a slope of 0, I'm now speeding up. So my slopes start to do what? They start to increase. So when I look at my velocity and I start to plot my velocity, what does that look like? Well, I start off at a large negative velocity, and then I go what? All the way to 0. And then I stop, and then I change, and I move what? In that direction here. So what you're seeing here is that in this case, my velocity was opposite of the acceleration. But now I've changed directions because I stopped, and this velocity and this acceleration are in the same direction. But look at the shaded areas. If you look at the shaded areas, look at this. If it's in this direction, it must be going where? It must be going left because it's negative. If I come over here, because it's positive, it's moving where? It's moving to the right. So that curve tells us that. And the fact that the acceleration in purple is always pointed in the positive direction, I have an acceleration that's a constant and positive. So those are the details of changing in direction because they happen in almost all problems. So we want to make sure that we nail these graphs